Now we're going to look at related rates. So imagine you're looking down on a map. Here you've got a police car, and here you've got a car traveling along a road here. And the distance from here to here is 100 meters, and from here to here is 40 meters. Now this here is the police car. This is any car here. The police car will have a radar gun. So the police sitting here will fire the radar gun at the car. Okay, so it will fire the radar gun, and then the radar gun will tell the police that the car is traveling at hang on at uh, at 30, let's just say 30 meters per second. But the thing is, it's traveling 30 meters per second in this diagonal direction here. Okay, so this unit, this 30 meters per second here is the speed of which is traveling in this diagonal direction here. But the thing is, the police really want to know what the speed is along the horizontal here. Okay, so the radar gun can only tell the speed in this direction here, in the diagonal direction. But what the police will really want to know is the speed along the horizontal here. Okay, so with related rates, you've got well, let's just say the distance here is d. What you have here is d by d of capital D over dt. So this here tells, this here is our 30 here, because it's saying it's traveling at 30 meters per second in the diagonal direction. So this 30 here, this is for the diagonal direction. But what the police will want to know is the horizontal. Let's just say x represents the distance here along the horizontal. What the police will really want to know is dx by dt. So this dt is per unit time, and this is distance. Distance per unit time is speed. Speed along the horizontal path here. This is the speed along the diagonal path. So with related rates, you're given something like this, but then somehow there's a connection between, well, this is a right angle triangle. There's a connection between d, x, and 40. And when given d of capital D over t, well, when given this here, you can work out dx by dt. Okay, because there's some sort of connection between capital D and x and this 40 here, you can work out dx by dt. Okay, or hang on, or when you look at let's say you've got a rocket. As far as this rocket is concerned, is traveling. Let's just say this is h, the height. Okay, as far as the rocket is concerned, it's dh by dt. So meaning that the rocket is traveling vertically upwards. But let's say you've got a camera here and you want to film the rocket. How fast should you rotate this angle? So as the rocket climbs, you've got to rotate your camera here. You've got to rotate the angle here. The thing is, as far as the rocket is concerned, it's traveling at 300. Let's just say 300 meters per second. So what you've got here is dh by dt, because h represents the vertical height, and the vertical height is traveling, if that makes sense. The vertical height is traveling at 300 meters per second in the vertical direction. So this 300 here represents dh by dt, and what the camera here is concerned about is the angle. How far should it rotate this angle here? Well, as far as the camera is concerned, it's only concerned about d theta by dt. So how fast should it rotate per unit time? So as far as the camera is concerned, it only cares about d theta by dt. As far as the rocket is concerned, it only cares about dh by dt. But then there's a connection by using Pythagoras or whatever. There's or trigonometry. There's a connection that allows you to, when given the speed of the rocket, you can actually jump to d theta by dt. Okay, so that's what related rate is concerned about. Translating from something like this into this, or maybe perhaps you want to know this distance here. So as far as the rocket is concerned, it only knows dh by dt. So as the rocket is moving upwards, you can actually calculate how fast well the well this capital D here is increasing each time. You can actually calculate the length at which it's increasing. Okay, and looking at this rocket scenario here, let's just imagine. Hang on. So remember, the distance here is 1 kilometer, 1,000 meters. Okay, from here to here, 1,000 meters. So the camera is here. Now look at this scenario. Let's zoom out. So when you zoom out, you will have this scenario here. So the camera is here. The rocket, let's say the rocket is here. So when the rocket has traveled 5,000 meters, this here, the rocket is at 10,000 meters. You can see that this angle here, this theta here, is much bigger than this beta here. So the point is that as the rocket travels further and further away, the rate at which the angle is increasing it slows down. But it is increasing, it slows down. The point is that as if the rocket's somewhere around here, theta increases by quite a lot. But when the rocket is up here somewhere, theta will increase, but by a tiny amount. Just bear that in mind, okay? All right.